Great. Welcome to Module 57, in which we talk a little bit about algorithmic bias and fairness frames. To some extent, we've been pointing in this direction throughout the semester, from basic data science towards models. The goal is always deployment, right? So this is practical data science. What happens when we take our statistics, our reports, and our models that can make predictions and put them out into the world and let them have an effect on the world. And we kept on coming back to all kinds of ethical issues. So this is to some extent going to summarize some of those concepts very briefly, but it's going to introduce a few more concepts that we've so far left just implicit so far. So by the end of this module, you should be able to explain 3 different sources of algorithmic bias. You should be able to define and compute 3 fairness metrics to some extent, or at least understand them at a high level. This is going to be demographic parity, equalized odds, and predictive parity. And you can do this from a confusion matrix technically, but just being able to differentiate these at a high level would be fantastic. You should be able to articulate the impossibility result. This is something that derives from those 4 different fairness metrics or fairness frames. You should be able to audit a simple sklearn classifier for fairness across a protected attribute, and you should be able to evaluate which fairness frame is most appropriate for a given decision context. So what is algorithmic bias? Algorithmic bias can also be described by a few different definitions, but generally it's a systematic and unfair skew in a model's outputs that disadvantages certain groups. And usually these groups are defined by demographics like race, gender, age, disability, some other personal characteristic. Okay, so there's actually 2 keywords here. Unfair is one of them. Unfair can be 2 things. It can be unfairly negative or unfairly positive. You could give too little or too few advantages to one group or another. But the other keyword is systematic. So it's, occasionally you're going to see, one group appearing to be heavily advantaged or disadvantaged for a particular experiment. And to some extent, the examples we're going to see today are just examples of that. Just because you measure, a little bit of a disparity for a particular experiment doesn't mean it's necessarily systematic, but it can still be an indication that it is. So we have to keep our minds open, and we have to look at all the evidence and keep on getting more evidence. It's not just that, we found this one instance where a member of this group had this particular kind of outcome, but if we see that same group consistently having a particular kind of outcome, then we need to examine further. So the keyword is systematic. So there's several ways that we can imagine bias amplifying. This graph comes from Fusar-Poli et al. At this link. They kind of show how models being introduced into the world sort of accumulate bias, and then this accumulated bias sort of amplifies and grows out of control. So normally the main issue is that, there's already real-world patterns of inequality. These examples mostly come from health. So health data tends to be historically pretty biased across groups, but this is true in other disciplines as well. But the idea would be that there might be a subgroup of people who are disadvantaged in the healthcare system, so all of the data that we have available to train our models in the first case exhibit that disparity. But then we collect the data from the real world, and this is the yellow phase over here. We set the sampling biases, there's patterns of bias that already exist, so the data now has measured these biases. Next, we have the AI design and deployment practices. For our purposes, this is going to be mostly just the models that we learn. So the data are biased, the models that you and I construct are so good because we're so knowledgeable in data science and machine learning. When I say good, I mean that they represent the reality of the world. You and I know better already, and certainly at the end of this module, we'll know better that we'll need to adjust these models to look for these discriminatory patterns in the first case. But imagine that for some reason we haven't yet, and we decide to deploy the model. Then this model that we deploy in the world to make predictions about whether this person should be admitted to the university or hired for a job or admitted into the hospital. It'll make decisions that will reflect internals of the model that are based on discriminatory data that were trained on real-world patterns of health inequality, and then it'll amplify those problems. So the new outcomes in the world will also be unequal amongst groups, and the pattern sort of repeats itself. So The three main sources of bias that we talk about are data bias. So the training set itself reflects inequities in the first case. There's model and design biases. So this is where proxy features will encode protected attributes. We'll see an example of this in a moment, but even if we try to be careful and remove like explicit references to race or gender and so on, other variables can still reconstruct those variables. Those are the proxy features. And if we're just trying to optimize things globally, like be as accurate as you can on average as a whole, then this very simplistic means of optimization can sometimes disadvantage certain subgroups. That's the second entry point for bias. And then the third is these feedback loops. So the model makes decisions that are biased, this produces biased data, and we kind of loop back to the beginning. There's an amplification over time. So the data is biased, the methods we use are too naive. We didn't take into account bias reduction, and we've deployed a model sort of too quickly. We've engineered a model too quickly. Here's a little note that I kind of touched on before, like not all bias, first of all, not all like noticed instances of bias are necessarily indicative of trends. Often they are, but not always. So that's something to keep in mind, which I talked about before. Secondly, a subtle difference is that not all bias is necessarily illegal. Just because something is not illegal doesn't mean it's ethically right. But it also, not all bias is necessarily ethically wrong, right? So consider something totally different. A spam filter should be biased, so to speak, against phishing emails, right? A system that is looking for a sickle cell anemia in patients might be biased to predict it more commonly in people with people of color, who are more likely to have sickle cell anemia than the people who are not of color, white people. So speaking loosely, sometimes there are decisions that ought to be made more or less frequently for one subgroup or another. So that would just be the right thing to do, because some subgroups are just more susceptible to certain things, not based on anything culturally, but based on the actuality. So we'll come back to those issues in a few moments. The hard question now we're starting to ask ourselves is, like, which systematic errors will be acceptable to us, for whom, and who decides these questions? Okay, so we're kind of popping ourselves out of pure data science, pure computer science mode right now. I think I framed this entire course from the very beginning to be, we are scientists working on scientific problems. We're engineers, meaning to ship the tools that we build into the real world very carefully and robustly, but also we're decision makers who work in multidisciplinary contexts with diverse stakeholders. So increasingly now, and in a few other modules previously, we need to think about our immediate environment, and these kinds of ethical questions are going to be super important. There are a ton of real examples here. Like I had many more slides here that I just trimmed down here, but there's examples of AI systems or computer science or data science systems exhibiting racial bias. So Compass was a system that tried to measure recidivism, estimate recidivism, so how likely someone is to commit or recommit crimes. And the study showed that, well, this Compass system was twice as likely to false flag black defendants as high risk compared to white people. Amazon famously ranked applicants containing words related to women as lower importance than those that didn't include these terms. There's a whole subsection of natural language processing and machine learning we can get into to describe why this happened and how we could algorithmically remove these kinds of biases. Amazon, I suppose, doesn't have very great engineers who work there, so they had this challenge. Maybe they have better people who work there now. Who am I to say? iTutor Group auto-rejected applicants over a certain age, and they had to pay a fairly large settlement for discrimination against groups based on age. This paper by Obermeyer et al. Is a great example of identifying racial bias in algorithms in health. They found that healthcare spending was a proxy for need, but spending also correlates with race and income. So it, if it turned out that black patients were sent home, therefore they didn't accumulate very many costs in the healthcare system, If treatments that cost a lot usually are associated with high risk diseases or treatments, but these patients were being sent home, so they weren't costing the healthcare system very much money. So therefore, if cost is the same thing as risk, according to a model based on data without much extra mitigation against bias, then it was kind of learned that, well, these patients who have these demographics don't have healthcare needs that are high risk, and then that was a problem. So race, like the spending, healthcare spending was sort of seen as a proxy for race, and that was a problem. Then there's also kind of interaction effects. So this other paper showed that sometimes there's interactions between multiple variables. So gender and race can somehow be multiplied together, to speak loosely, to amplify bias. So in this case, they showed that error rates could be, for facial recognition, we're up to 35% for dark-skinned women in particular, compared to less than 1% for light-skinned men. So there seemed to be this amplifying effect of these two demographic variables that made error rates very bad for this particular subgroup of people. And I could go on and on for a very long time. It's not hard to find other examples of this yourself online. All of these systems seemed to perform well overall, right? And this is the key kind of insight here. You can have a system that has a very high accuracy on average. If you have like one measure in one table that says, well, this system works very well, like the accuracy is 95%. So it seems to be doing very well. Another system only performed at 90%. Therefore, our system must be better. Therefore, we should deploy it. We kept on coming back over and over in this course over the need to compute aggregate metrics of different types over different subgroups to identify whether or not any subgroup of people based on any combination of variables might be disadvantaged. So this is more or less the anti-example we've been pointing to. Imagine that we're a data science team, you and I, and we're going to build a loan approval model. Like we work at a bank and we're going to see whether or not this application deserves getting a loan or not. And we know that we don't want to make a decision based on race because we're concerned that, well, if the model picks up this particular race variable, it might end up learning some bias that we don't want. So we just literally take that column for all of the applicants that we might have encoded race on and just delete it. So we don't have race anymore, and we should be fine because the model doesn't have this data anymore. The problem, as I pointed to a moment ago, is that there are proxy variables. These are other variables that ostensibly measure different things, but those other things that they ostensibly measure are highly correlated with the demographic variable we've tried to remove. So zip code, maybe a school name, maybe how many years you've lived at a current address. Each of these variables might actually be highly correlated with race or socioeconomic status, to an extent to which you'd be able to reconstruct these variables. So maybe socioeconomic status is another variable you meant to delete. But if you find out that someone is living, in the south end of Halifax, like on Yonge Street, then this might be an indication that they're relatively well off. Or if they're in the Bridle Path in Toronto, that's a good sign that they're relatively well off. So you have their address. Technically, people from any racial background can live there, and technically anybody from different socioeconomic groups can live there also, but it's very rare to see someone someone well off who lives in a low-income neighborhood or vice versa. If that makes sense. So if past loans were actually approved at different rates for different demographic groups, different racial groups, different socioeconomic groups, then this model could learn to detect that or to learn a model that mimics that behavior, even if it's only given the proxy variables as input. And then therefore it's deployed and then it has an impact on the world. US law, to the extent that it exists, and even common sense ethics, to the extent to which it exists, often evaluates like outcomes, not just inputs. So we care about the equality of outcomes, not necessarily like the equality in the data that we're given, although there's all kinds of counterexamples to that. So what we'd call a race-blind model that approves white applicants at 3 times the rate of equally qualified black applicants would be considered to be discriminatory, obviously. But obvious to us because you and I have common sense ethics. If the outcomes are drastically different, it kind of doesn't matter what the inputs to the system were. The effect of the system is what we care about, and that's normally when you say care about, I mean in a legal context. So the main moral of this story is that it can be kind of naive to just simply remove a sensitive column of variables and say we've mitigated against racial bias or any kind of other bias. That's not going to be the case. We have to look for proxy variables, any variables that are highly correlated with the variables we're trying to remove, and we also want to be able to measure outcomes by different groups, different subgroups. Let's dig a bit deeper. So for this module, we'll talk mostly about binary classifiers, and there's 3 different variables we need to think about here. Okay, the first one is the protected attribute. We call this A for attribute. For now, let's just imagine there's only 2 of them, right? So this can be, like, without getting any specific here, group A would be encoded as 0, and another one would be 1. So maybe A is I don't want to mention any demographics, but because every demographic you can mention, there's a case to be made that there's more than just 2 instances, 2 values for those variables. But imagine there's some protected attribute A, either you're in group 0 or you're in group 1, just for simplicity. But this generalizes to A being 0 or 1, 2, 3, and so on. There's a true label, so we're doing binary classification. So for this particular data point, we know the truth somehow. Like we know from this particular loan application, they actually repaid the loan, 1. We also might know that they didn't repay the loan, which is 0. So we have the true label, which we talked about at great extent during the modeling phase of this course. But then we have the model prediction y hat, which can be 0 or 1. So we're trying to estimate what the label should be, but we could make a mistake. So y doesn't always match y hat. We previously introduced the idea of a confusion matrix. For a binary classification task, there's 2 possible actual labels. The truth, it can either be true or false, and the prediction can also be likewise true or false. And then we have, for each of these 4 possible combinations of these variables, we have these counts for how often we observe these pairings in our data, in our evaluation data, when we're doing testing for potential deployment. So like a true positive, for example, would mean that, well, we predicted positive, and it truly was a positive. That's a TP true positive. A false positive would mean that we predicted positive, but that was false. So the label was 0, we predicted 1, so this is a false positive. We talked about this previously, so I don't need to get into it again. So we have different means of looking at distributions here. We have true positive rate, which we called recall. This is the number of true positives versus all of the instances that were classified as positive. We have the positive predictive value, which we called precision. This is the number of true positives given all of the things we predicted as positive. So I got those reversed. Precision is out of all the things we predicted as positive, how many of them were actually positive, and recall is out of the things that actually are positive, how many did we predict were positive. And then false positive rate is how many false positives do we have divided by false positive versus plus true negative. So we have 3 fairness frames I want to introduce, and this will ask which of these metrics should be equal across our groups. So the first frame is demographic parity. This is a metric of fairness across groups. Sometimes demographic parity is called a statistical parity or equal selection rate. And it basically means this. The probability of predicting 1, given that the person belongs to group 0, should be equal to the probability of predicting 1, given that they belong to the other group 1. When I say equal, I mean this is approximately equal for some definition of approximately, but this is what we're aiming for, equality. So we have both groups are approved, or flagged, or hired, or admitted, or whatever the positive label is, at the same rate, regardless of what the truth is. So I don't really care if this person in group 0 or this person in group 1 will actually repay the loan or actually be hired or actually be admitted to the hospital. All I care is about the rates of positive prediction. They should be approved at the same rates. Okay, so to some extent, maybe if you mentioned, as you can see here, like there's no value of y here. I'm looking at the probability of the prediction given the group, but I don't care what the truth is. So there's no like y here. There's no true label anywhere in this computation. So this can make sense if you believe that the opportunity itself should be distributed equally. So across these two demographic groups, people should be, like outcomes should be equal, regardless of anything else. And this makes sense if the historical base rate differences in the past data reflect some kind of discrimination rather than any capability differences. If we assume that, both men and women, again, assuming those two groups, are equally skilled in terms of engineering, we should not care about whether or not a man or a woman actually was hired for a job of man or woman in the past. We should offer them the job at equal rates. But this can be problematic, so this is not a perfect measure. If the groups genuinely differ in the relevant outcome, then forcing positive rates will distort the clinical care. I mentioned sickle cell anemia, which is much more common in black patients than white patients. So if I have a sickle cell anemia predictor, and I'm saying the probability of being diagnosed with this disease is equal, whether you're in group white or group black or vice versa, that might be wrong because, like, just genetically, these two groups do have different base rates. There's nothing to do with form or cultural bias. Breast cancer does occur in men and women, but it's much more common in women. So if you're doing a breast cancer prediction engine and you're predicting positive rates for the two groups, men and women, or women and men, that the relevant outcome, the true labels matter, and we're forcing equal positive rates that might distort clinical care. So this works in a lot of situations, maybe for offering jobs for groups that deserve them equally, but sometimes it doesn't work. So I want you to think for a moment and maybe even write down this particular use case. If a university accepts students at the same rate from every school district in a region, regardless of grades, regardless of how well the students are performing, is this fair, right? So maybe there's one school district where grades are very high, another school district where grades are very low, but applicants from these two school districts are accepted at the exact same rates. Their outcomes are going to be the same for this prediction. Is that fair or not? And just to seed your thinking a little bit, this can depend entirely on why the grades differ between these districts. If there's some underlying bias that forces students of the same caliber or capability into schools which are funded to different amounts, then you're measuring something to do with the funding that the schools received, which amplifies or de-amplifies the grades in a way that ignores the true value of the students themselves. So I'll leave that for you to think about a little bit. That's our first frame, demographic parity. The second frame is equalized odds. This is one that my research touches on more commonly. And here's a paper that describes it in more detail. Here we still care about the probability of outcomes, the probability of a prediction being positive or not. In this case, we still want the rates to be equal across the two groups. So whether the attribute is 0 or 1, whether say the race is this or that, or the sex is that or that, assuming two possible values for each. Well, we also care about base rates. So we say, well, given not only the group attribute, which can differ, but also we care about the actual label being true or not. Okay, so another way of saying this is that the true positive rate and the false positive rate should be equal among groups. Or to say this even more directly, among the people who truly qualify for a loan, that's the true label y is 1, both groups, a equals 0 and a equals 1, should be approved, that's y hat equals 1, in both cases, at equal rates. Or for people who truly don't qualify, like they don't repay their loans, so y equals 0 in both cases on the left and right hand side, both groups, a equals 0 or equals 1, it doesn't matter, should have outcomes, predictions, y hat, being positive at equal rates. Okay, so here we've basically taken the demographic parity from this slide, and we've just inserted that actually we do care what we're given in terms of the true labels, y. So in this case, the strengths are we respect the true label. We're not penalizing one group for having a higher base rate than the other. So we're not assuming that men and women should be diagnosed with breast cancer at the same rates. We can take advantage of actual base rates to make to ensure that we're trying to hit this equality. So this will capture like the most common discrimination concern. So it doesn't matter if you're in group 1 or group 0. What matters is like the truth of the matter, which is this y factor, which we're including in the condition. I mentioned COMPAS before. So COMPAS failed equalized odds. It had higher false positive rates for black defendants. This is the recidivism detection system. And so it had a higher false positive rates for black defendants. So there was truly low risk people, but it was classifying them as high risk. So it was kind of ignoring this, this condition y equals y. Finally, predictive parity or calibration. This only differs in the sense that we've kind of swapped the true label and the prediction. So now we're looking at, well, among the people we predicted as being part of class 1, how many of them actually belonged in class 1. So subtly, it's similar but different. In this case, we're not conditioning on the truth of whether people deserve to be classified as 1 or 0. We look at how they are actually classified, and then we kind of go back and check, whether or not they match those predictions or not in the true labels. Another way of saying this would be among the people that the model predicts will succeed or reoffend or whatever the prediction label 1 means, the same fraction actually does in terms of the true labels in both groups. So this ensures that the model scores, the predictions of the models mean the same thing regardless of group, which is going to be important for trust and decision making and so on. This COMPAS creators argued that their tool did satisfy this condition. So they were basically saying, well, if we're making predictions about high risk, then the truth of the matter in the labels were the same. So this probability distribution actually matched. This is not going to, we're not going to go into much theory in terms of probability and statistics and conditional probabilities. We had a slight introduction to this, and we looked at Bayes' rule. If you remember Bayes' rule, that's where you can express the probability of one quantity given another. You can express that as a probability of the other given the first quantity with some other prior probabilities thrown in. So North Point, the makers of this COMPAS tool, actually suggested that, well, even though we failed frame 2, we failed the equalized odds measures of equity, we actually matched predictive parity. So we were good from this perspective. So as you're about to see, satisfying this calibration frame, while the groups have different base rates, actually forces the false positive rates to differ. So again, going back to one of the main messages from a previous module, if you ignore the priors, then your predictions can be faulty. So just because this metric was satisfied, it doesn't mean that the overall acceptability of the system was satisfied. Here's a little bit of an interesting pseudo-paradox. Pseudo-paradoxes come up all the time in data science and probability. Suppose you have groups with different base rates. So a group A equals 0 and group A equals 1. They have a probability of having a score y equals 1 in both cases. But in terms of the truth, these probabilities are not going to be the same. The base rates of group 0 having positive outcomes and group 1 having positive outcomes are actually supposed to be different. They're supposed to be different. The result here, the claim anyway I'm making, is that no trivial classifier will be able to satisfy each of demographic parity, equalized odds, and predictive parity. So one of the issues with COMPAS was that, well, they said we satisfy predictive parity, but we don't satisfy equalized odds. And part of the reason why that's the case is because they had different base rates that weren't part of these formulations up here. These are only the conditional probabilities without any the prior probabilities, so the sheer probability of y's in the first case. Okay. Why is this the case? Why can't we satisfy each of these metrics simultaneously, trivially? Well, the three constraints, 1, 2, and 3 here, these three frames, form a system of equations in our confusion matrix. And when the base rates differ, then satisfying any two means you've violated the third. So you might be able to match demographic parity and predictive parity, but you won't be able to match equalized odds. This won't always be the case, but there are going to be situations where it is the case, where base rates differ. Okay, so you can. Well, we'll see this in a moment. So I'm going to show you an example of this in a moment. The main emphasis here is that this is not a software bug. It's not like it's not necessarily a software bug. Software bugs do happen, and they can result in these frames being differentially satisfied or not satisfied. But it can just be a mathematical fact if you ignore base rates, if you ignore your priors. So the main concept here is that if you want to choose a fairness frame, if you want to choose one of these, you say we're going to measure a fairness frame to see whether or not our model is biased or not. You can choose one or the other. There's mathematics behind each of these, obviously, but it's not just pure mathematics. It's not just a pure technical selection. How you approach values and ethics also will matter. Let's see some examples. So here's a simple example where we have two groups, and we have, say, 100 samples from each group, and we have a model that's making predictions for each of these groups in a binary classification task. So we have accuracies of about 70% in one group and 65% in another. There's a slight bias, in favor of group 0, but a difference of 5% in some cases is not big enough to make an issue of it. A lot of instances, we're going to see these systems deployed with this kind of disparity. If we scratch a little bit further, we'll see that, well, the recall for group 0 might be 80%, and the recall for group 1 is 75%. So we can see that, well, for all of the instances where class 1 should have been measured as class 1, this more or less is balanced across both of these groups. So we've kind of, the recall is the same, our true positive rates are equivalent, roughly equal, and we're more or less satisfied. So the accuracy is very similar, the selection rates are similar, true positive rates are very similar. False positive rates, we defined that a moment ago, 40% for one group, 37.5% for another group. These are almost identical. So far, like each of the metrics we've chosen to look at seems to suggest that group 0 and group 1 are more or less fairly balanced. But suddenly you look at PPV, and this is what we called precision previously, and you'll notice that, well, of all the individuals who we flagged as positive in group 0, about 67% of them were actually class 1. All the people we flagged as class 1 in group 0 were actually class 1. And all of the individuals from group 1 that we flagged as class 1, only 33% of them were actually class 1. The predictive parity here is clearly violated. Again, it depends on what your thresholds are, but a difference of an entire third over here between group 0 and group 1 is fairly large. You can look into how we formed these rates over here. We just kind of constructed these fictional confusion matrices directly. So, a data scientist who didn't take this class, I don't know how you could miss. Maybe other universities don't teach you about ethics and about more than just accuracy in terms of metrics, but a pseudo data scientist who only reported overall accuracy would miss all of these other measures, and would especially measure that there is some clear disparity between group 0 and 1, and that disparity is in terms of precision. I can kind of visualize this here, so this is more or less the same thing. If you just look at overall accuracy of approximately 70%, this could hide these gaps. In particular, here's the PPV gap of approximately a third, of 34 percentage points. So group 1 applicants who are approved are half as likely to actually succeed in this model. This model's positive label means something different for each group. If the outcome is a positive outcome, it's like a good outcome, then great for them, I guess. They seem to be unfairly advantaged. but obviously that's not fair, so we want to avoid it. Here's a second example. Here we're actually going to perform a little bit of actual logistic regression. So here we have some data. In this case, we'll have a couple of data points, x1 and x2, and these will be highly correlated with a signal, which is biased across our demographic groups, group 0 and group 1. So we collect more or less 300 samples from each of group 0 and group 1. Through this process, even though we're not including this signal, which is biased, it's a weaker signal for group 1, as you can kind of estimate here on line 15. We're not actually explicitly including it, but we're passing variables that are highly correlated with that biased signal into a simple logistic regression model, which we saw previously. We do scaling, we fit it, we train it, and then we do our predictions, and then we do our auditing. So this is an actual instance with real data now. I mean, it's still a toy synthetic data, but it is real data. You can see, even though we're not, this is the issue of proxy, even though the group or the signal that is highly correlated with group is not actually given to the model. There's a couple of different fairness violations. The first one is, well, there's an unequal true positive rate. Group 1's positive examples have a weaker feature signal because these measurements were designed mainly on, or standardized mainly on group 0. So the model catches fewer of group 1's true positives. So we have a big bias in true positive rates. We also have unequal PPV, or precision, like we saw a moment ago, because the base rate is still lower for group 1, and the signal is weaker. A positive prediction for group 1 is less reliable than group 0. So if a positive classification is made, only about 36.6% of those instances ought to have actually been labeled as class 1, whereas almost 80% of positive labels for group 0 were actually labeled as or should have actually been labeled as positive. So in a super simple example, again with only a few variables here, just because of different base rates and variables that incorporate proxy variables to the group, we have a ton of disparities going on between these two groups. And you can kind of see this same metrics over here, both in a histogram and in this bar graph, which basically just plots true positive rates and false positive rates. Group 1 is lower and to the right on this plot. This isn't a full rock plot, like we talked about that previously. These are just two instances here. So we have a higher false positive rate for group 1 and a lower true positive rate for group 1. These are two different metrics, which aren't necessarily inverses of each other. But there you go, group 1 is pretty disadvantaged. So even though, actually, one thing I didn't include here was overall accuracies. You can enter into this line over here, another line for accuracy. I had it and I removed it. So maybe as an exercise, add another line for accuracy. Try to remember how to measure accuracy in terms of the measures from the confusion matrix, and then plot accuracies. But actually the accuracies are very close to each other. They're both, they should be pretty close to each other. The model is going to basically catch about 1 in 3 of group 1's true positives and only catching 3 in 5 of group 0's. So equalized odds is not satisfied, it's violated, and so on. So whose fairness counts? So we had 3 different frames measuring fairness in these slides. We had demographic parity, which was the first one. This is where we were just looking at sheer outcomes and we didn't care anything about true labels. So if you had groups with lower opportunities in the first case, then demographic parity might actually protect them. If people from certain demographic groups weren't offered jobs because of cultural biases that we want to now erase, and we don't really care too much about base rates in those groups historically, from biased historical data, we'd cut out the true label and then just use demographic parity for our fairness metric. But this could penalize groups with genuinely different outcomes. So we talked about sickle cell anemia belonging more as a diagnosis for one group versus another. So there was an actual signal there that wasn't just based on cultural bias or breast cancer, or you can come up with others your own. So we need to integrate true labels into our fairness metrics, and they occur both in equalized odds and predictive parity. Equalized odds, the true label is part of the condition, so we care about the probability of a prediction being positive, given that it should actually be positive, and we don't care about whether it's group 0 or group 1. The rates should be the same. So in this case, we'd protect people who actually truly qualify. We'd make use of something that's like the true label, which we can assume to have been acquired through non-biased means. This might penalize overall accuracy. You'll see a lot of research papers, including some of the ones that we cited, that when they introduce metrics that make these metrics be fair, overall accuracy might be worse. But the result is that we've made sure that the different subgroups more or less have similar rates. Usually accuracy drops by a few percentage points overall on average, but it's raised by dozens of percentage points for individual subgroups. And then finally, predictive parity, we kind of just swap the position of the true label and the predictive outcomes in our conditional probabilities. Here we care about what is the probability that actually this person should have been labeled as a 1, given that they were labeled as a 1. So we're given the prediction, we want to make some kind of claim about the prediction. We want to protect trust in the score itself. But like we saw previously with the compass example, sometimes you can have a strong predictive parity, or predictive parity can look good, but this will penalize groups with lower base rates. The North Point was sort of ignoring their priors, and those priors sort of were implicitly part of equalized odds. There's a connection between these two metrics, which I mentioned, that you can form through Bayes' rule, which we saw previously, but that's just a side note. So choosing which of these frames should be the one you're trying to consider. This is a policy decision. It's one based on a lot of factors. It's not a simple machine learning one or data science one. You have to consider your stakeholders, affected communities, domain experts, your legal team, presuming your environment has a legal review team. So it's not just simply a matter for the data scientists. There are a ton of mitigations. In fact, mitigations are what I like most about how we approach bias. Bias exists, and people get their back up and they get very concerned. Oh no, machine learning can produce biased outcomes. Of course it can produce biased outcomes, but there's a ton of tools that we can apply to shave off the bias and make, despite what we've learned, to kind of force those metrics to be as equal as possible. So there's tons of ways that we can balance things. It's not a lost cause. For now, I'll just mention that we can report things. So the examples we saw today show that we're not just reporting accuracy, we're looking at a bunch of different metrics. And so precision and recall is the one that I'm focused on mostly here. So measuring precision, measuring recall, which we've seen several examples of, are a good way to examine subgroup disparities as long as you measure them for each of your subgroups. Fairness audits. So if you're actually part of a team and you're going to deploy a model, then having a team actually try to measure these things in the first case and relate these metrics, precision, recall, against things like credit, hiring, healthcare, justice, should be part of it. Sometimes, we have showed a loop where we showed all there's 3 different places where bias can come into the system. And sometimes the best thing to do is to go back into the actual data and consider how we're modeling the data generating process itself from the beginning. So it's not merely a measure of, it's not merely measuring, and it's not merely applying those mitigation techniques, which we didn't get a chance to really talk to in this module, but it's looking at the big picture as a whole. So one of which is this one of the entry points for bias is these feedback loops. So many machine learning systems are not merely deployed once and then frozen, and then we're going to use these systems forever going forward. Rather, a model is deployed. The model will make decisions. So it'll make a decision as to who to admit into the university or who to give a loan to. We have all of our familiar examples. But then the real world will have labels applied to them. This person was actually given a loan. This person was actually admitted to the university. And then those data points and labels will now form a new training data set that we can use to retrain our logistic regression or whatever model we're using. And then that's one of the entry points we described earlier for bias to enter into the system. So there's various things you can do. There's we call it predictive policing. This is an example before we get into the mitigation. A model trained on historical crime data could predict high crime zones. Maybe there's a particular area of Halifax where crimes were just simply more likely to occur. But then the police end up sending more police officers to those areas to patrol those zones. Because there's more police officers in those areas, they're more likely to see instances of crime than if they were patrolling areas where there were historically lower crime rates. So more arrests are made in these areas because more policing is there. And then the model trained on that data will see, well, look, all these arrests are happening in these particular areas. We need to send more police officers to those areas because that's where all the crimes are occurring. But we're obviously not measuring crimes that we're not measuring crimes that weren't observed in the first case. Crimes can occur in other areas with potentially just as high rates, but they're never caught because the police officers aren't there to measure them. So we'd never know things that we just wouldn't measure. So under-policed areas would appear to be safer even if they actually were not safer, simply because no one is looking. I'm not a social scientist, but there's tons of instances of this happening. And unfortunately, often in the first case, and because of other instances also, this is a bit of a simplistic view of it, but there might be other sources of bias that enter into this little loop over here. But certain areas will be cracked down on in a way that others aren't, and this will just reinforce itself in a way that is increasingly unacceptable. So there are mitigation strategies, there are audit models, there's causal thinking. So would a change in group membership, if everything else is equal, change the prediction? There are counterfactuals, which are related to causal thinking. What would have happened if this variable was different, and then you make a prediction on that basis. So if this crime, if we swap area 1 for area 2 and see if the prediction is the same, or if you switch a demographic variable if it's available from one to the other, see if the prediction is same. This is sort of causal thinking or counterfactual thinking, and I might be able to post some links to papers that describe this. This is a bit beyond the scope of a first-year class, but that's one mitigation strategy. And human-in-the-loop designs. I don't always trust humans. I think humans can be just as biased as machine learning systems, if not more. But we need lots of eyes on these systems from lots of backgrounds to ensure that these models are being deployed fairly. There are various toolkits. This might be some place where I ought to have put the microscope over here because I'm not going to test you on these. This is more for your own knowledge. So I'd encourage you to look at FairLearn and IBM AI Fairness. These are two corporate toolkits, but they're fairly robust and decent regardless. So FairLearn computes fairness metrics for you. There's mitigation algorithms, again, which we didn't get a chance to talk about. So FairLearn from Microsoft offers that. IBM AI Fairness 360 offers a ton of bias metrics. And I think they're even cited in sort of standards documents like from NIST or in SEC, for example. There's means of using explainable AI, which again is beyond the scope of this class, to open up the models and examine why they're making the predictions, and then to use that answer to the question of why they're making predictions to potentially spot proxy variables, like the zip code, or in more appropriate terms, postal code is more has a huge influence on the prediction of whatever it is we're deploying. And model cards. This is a great paper. It comes up constantly. Model cards is a way of sort of documenting models that are to be deployed. It's relatively standardized. It comes up a few times, or modifications to it come up in like ML ops or machine learning operations toolkits. Again, this simply documenting the process can help to elucidate problems with that process. In later classes, so fairness comes up a lot in the CSCI 3151 at Dalhousie, and whatever is equivalent at other universities. We're also going to be offering a fourth year responsible AI course going forward. There's other courses we offer online at Dalhousie that dig deeper into these topics and also get into mitigation strategies. But we're going to see this over and over again in ways to, post-process decisions in order to make them more fair from, say, equalized odds perspectives. And there's a ton of techniques at our disposal that you'll see later. So I keep on coming back to this, but I think it's really important. The models we build will be trained on data about real people, almost certainly, and therefore when you deploy them, they're going to affect real people. The skills we've learned in this course, so group by, mean, confusion matrices, a lot of them will come up quite a lot when you're doing exploratory analysis for fairness audit. So all of the things we've seen throughout this entire course are tools you're going to be using when you're doing fairness auditing or bias reduction. So you know quite a lot, so I'm very happy for that. But again, be curious. We've only scratched the surface for a lot of these techniques. The 3 questions I want you to ask yourself before you're deploying any classifier in the real world is, who is in my training data? Who is missing? How can the data collection process itself have introduced bias in the first case? The model error I'm computing, what are the real world costs, and for what groups do we have costs? Are there costs in true positive rates, false positive rates, precision recall? Consider all of those things. And also from the real world perspective, maybe from the insights from stakeholders, what benefits or biases can occur in the world if we actually deploy this model. And just simply asking these questions is cheap and easy, but it's expensive if you ignore them. I think I mentioned this in course also, but you might have seen in medicine, in other disciplines, students are put through very rigorous and very challenging scenarios in order to get their degree. And in other disciplines, it's nowhere near as personally challenging as it is in, say, medicine. And I think a lot of the reason why that's the case is because people recognize that medicine has a ton of real-world consequences if you get it wrong. It's literally life and death in many situations. So med students are put through the ringer, so to speak, in their education. And even though I think to a large extent we've only covered a lot of these topics very superficially in this class, I know that other ways that we could have learned data science could have been far more superficial than what we've seen so far. And I just wanted to emphasize that I think that would be the wrong approach, because now more than ever, and increasing every single month and every year, data science is being used to make decisions about who gets the job, who gets admitted to surgery, or who gets real world outcomes. Data science is the means by which our lives are increasingly run or ruled or affected these days. So it's not just med students who are making life and death decisions, it's you who are making these decisions also. So I can't emphasize enough how important it is to subject yourself to challenging circumstances when you're learning about data science. And if you want to just go through data science with your eyes half open and not challenge yourself, then that's going to be a big problem for the world at large. So again, even though to a certain perspective, we've only kind of touched on some topics at a very high level, I understand this is only a first year course, and sometimes it can seem that there's a lot here, but I can't emphasize enough how important it is for you to get this right, for you to get the training of machine learning models and their deployment right, because it's certainly going to have an effect on people. That's the end of a little rant for today, but I truly mean that. So as always, here's some quick checks for you to go through for your own comfort. For the content, I would advise you to look at some of these references. As always, it's been a pleasure. Thanks so much. See you next time.